Hello and welcome to Pep Talk with me, Mr. Pepperell. Today I'm hanging around this farm thinking about heat transfer, and I'm wondering how is it that the radiator of this tractor keeps it cool, but my cup keeps my coffee hot? By the end of this video you should be able to say what design factors affect the rate at which an object transfers energy, and what can we do to control the rate of energy transfer from an object. So previously we found out about the different ways in which energy in the form of heat can be transferred, but now we need to know about how we can affect this process. So for example, you might want to transfer heat away from your laptop to stop it being damaged by being too hot, but at the same time you might want to stop heat being transferred away from your cup of coffee so it's nice and warm and appetizing. So let's think about cooling things down first, and a good example of how engineers have thought about heat energy transfers is the radiator that we saw in the front of the tractor just now, or in the front of a car. Okay, and we can see here from this image that the engine of a car gets really hot when it's running, and they're actually kept cool by pumping water around them. Okay, and this carries the heat away from the vital engine components. But how is that heat energy then transferred away from the water again before it's recycled back into the engine? So hot water from our engine flows into our radiator. The radiator then transfers the heat energy away from the water, okay, and cool water can then flow back out of the radiator to be recirculated around the engine. And the reason the radiator is so good at doing this is one of its properties is it's got a very large surface area. The surface of the radiator is actually made up of lots of tiny metal fins that are all in contact with the air, and it's from the surface of these fins that the heat energy is transferred away from the radiator, either by convection, the air around the radiator heats up and then rises away, or it's radiated out, hence the name radiator. Okay, and both of these two things serve to cool the water down. The bigger the fins on the radiator, the quicker the water will cool. So it's from this that we can actually see that it's the shape of an object and its surface area that affects the rate of energy transfer. Okay, make a little note of that. You may also know that engines include a fan that maintain a constant supply of cold air flowing across the surface of the radiator to accept and carry away that heat. It needs to be cold air. Okay, and from this we can say it's also important that the bigger the temperature difference between an object and its surroundings, so we've got a really hot radiator and there's cold air coming across it, the faster the rate of energy transfer will be. So if we've got really cold air, the energy is going to be transferred away from that radiator a lot quicker, keeping the engine cooler. So that's cooling things down, but what about keeping them warm by preventing heat energy transfer? Well, a perfect example of a product designed for this purpose is this thing here, which is a thermos flask. Now, the thermos flask is a brilliant piece of design. Everything about the flask prevents heat energy transfer. So, firstly, if we start on the inside and work our way out, we've got our hot coffee in the middle there, and the hot coffee is inside a double-layered glass bottle. Okay, now one thing we know about glass is firstly that it is a brilliant insulator. Okay, so that's going to prevent heat loss by conduction. And you'll also notice here that the glass is silvered on the inside. So what that silver is going to do is going to reflect back any heat which is radiating out through. Okay, now between the two layers of the glass bottle, what we've actually got is a vacuum. That's why they're sometimes referred to as vacuum flasks. Okay, now you should remember that heat energy to be transferred by conduction or convection, it needs particles to transfer the kinetic energy to. In a vacuum, there are no particles, okay? So what this means is that energy transfer by conduction or convection is very hard. It can't take place, okay? It's the same sort of principle for my coffee cup we saw at the start of this video, and the corrugated ridges in the cardboard have got air pockets inside, so it's much harder for the energy to be transferred through the air by convection than it would be simply by conduction through the solid cardboard. And of course, it's much harder for the heat to be conducted or convected through the vacuum when there's no particles. So the vacuum here is a really good way to stop heat energy transfer. Okay, finally, we come to the outside of our flask, which is made out of plastic, and we know that plastic is a very poor conductor, or again, it's a really good insulator, so that's another good piece of design there. And finally, up at the top here, we've got a plastic lid, and we've just said really that plastic's a very poor conductor of heat, and it also prevents evaporation from the top of the flask. Okay, now being a good insulator doesn't stop heat energy transfer completely, but it certainly slows it down. So from that we can see that the material an object is in contact with, so here our hot coffee is in contact with glass there, okay, the material it's in contact with affects the rate of heat energy transfer. If we had our coffee inside a metal container, that would conduct away the heat quickly. Because it's inside a glass, then a vacuum, then a plastic container, that's very hard for the heat to be transferred away, keeps our coffee warm. So let's just look at a couple more examples to summarise what we found out. What have I got here? Two foxes, but different foxes. I've got a desert fox here, he wants to cool down. I've got an Arctic fox over here, and he wants to stay warm. And evolution has selected their body shapes to do just that. Our desert fox has got ears that are shaped with a large surface area in order that he can lose heat quickly away, whereas our Arctic fox has got these small round ears to decrease the rate that he loses heat at. So one last example of energy transfer, this time by human design. We'll go back to our laptop. We saw at the start that we want to cool down. Okay, if we don't cool it down, some of the valuable components inside are going to be damaged. It's not going to work anymore. Well, what we do is attach these things here. These are called heat sinks, and these are fan-shaped metal plates that have a large surface area for them to lose heat from. Okay, we can also see that they're coloured black, and we know that black is the best emitter of infrared radiation. Okay, and they're also made of metal to ensure they quickly conduct the heat away from the valuable components inside. So this is a great bit of design here. We can see that we've got black surfaces, good emitter, large surface area in order for a lot of heat to be lost from, and metal, which is a good conductor to take the heat away and transfer it where we want it to be. So that is what we need to know about energy transfer by design. Any problems with that at all, don't hesitate to tweet me at Mr_Pepperell or email me and I'll get back to you ASAP. Thanks for stopping by.